Today we're going to be talking about molecular and empirical formulas. Our objective and essential question for today are to be able to describe and determine a molecule's molecular and empirical formula. And the essential question you all should try to answer in the summary of your notes is how can we use molecular and empirical formulas to describe the composition of molecules? Again, anytime we are flipping through these slides on these videos, please pause it and take as much time as you need to record what is on the slides, especially those slides with this little handwriting icon in the top right corner. So when we're looking at empirical and molecular formulas, our molecular formula typically describes the actual amount of atoms in each element. And our empirical formula, in contrast, will describe the ratio of atoms in each element. So let's talk about what that actually means. Here I have cyclohexane, and its molecular formula is C6H12, which means there are 6 carbon atoms. Let me write those 1, 2, 3, 4, 5, 6. And there are 12 hydrogen atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have literally just counted up the number of carbon atoms, and I've counted up the number of hydrogen atoms and created the molecular formula for cyclohexane. However, the empirical formula describes the ratio of carbon atoms to hydrogen atoms. So let's just take one of these. So you can see actually for every 1 carbon atom, there are 2 hydrogen atoms. So that's how I get my empirical formula. Another way of doing is looking for the common denominator of the subscripts in the molecular formula. So if I'm looking for the common denominator between 6 and 12, that is 6. So dividing 6 by 6, I would get 1. And dividing 12 by 6, I'm going to get 2. And that's our empirical formula. Let's talk about another molecule. What if we had methane? Now, in this case, we have 1 carbon atom, and we have 4 hydrogen atoms. 1, 2, 3, 4. So this is our molecular formula. It is literally telling us there is 1 carbon atom and 4 hydrogen atoms. But this is also our empirical formula. And this makes sense because the common denominator, I'm just going to add a 1 here so you all can see the math. Our common denominator between 1 and 4 is simply 1, which gives us our molecular formula again. So C1H4 or CH4 for simplicity is both the molecular formula and the empirical formula for methane. Let's talk about how we would write molecular formulas. Again, I encourage you all to pause this video and take a moment to write these steps down before I go over them. Okay, so the first step is to write the elemental symbols for the elements in the compound or the polyatomic ions. So here in this compound, I have sulfur and I have oxide, which from the elements, that is oxygen. So our elemental symbol for sulfur is just a capital S, and our elemental symbol for oxygen is a capital O. Now this one is nice and easy because it actually gives us those prefixes. This is a covalent compound, and step number 2 says use prefixes to add subscripts for the number of atoms in covalent compounds. So if we were to look on our prefix table, you would see that di aligns with 2 atoms. So if I have di, that means I have 2 atoms of sulfur, and then I'm going to write a 2 to indicate that I have 2 atoms of sulfur as my subscript. Now tri aligns with 3. So think of like a tricycle or a triangle has 3 sides. That's where those prefixes are coming from. So tri is indicating that I have 3 oxygen atoms. And that is my molecular formula for disulfur trioxide. Now let's talk about magnesium chloride for another example. So my elemental symbol for magnesium is Mg. My elemental symbol for chloride or chlorine is Cl. So I've written these out. I don't have any prefixes because this is an ionic compound. Magnesium's a metal and chlorine is a non-metal. Now I need to check for unbalanced compounds if it's an ionic, check for unbalanced charges of ionic compounds. So typically when chlorine has its octet full, it has a -1 charge. And magnesium, since it's a metal, it typically likes to give away. It has 2 valence electrons. It likes to give these away to form ionic bonds. So typically, magnesium has a +2 charge. Now we need to make sure that this whole thing, the charges on this compound add up to 0. So if I have 1 magnesium and 1 chlorine, then I still have a -1 charge. So in order to balance this out, what I actually need to do is add a second chlorine. Now I have that +2 charge from magnesium, but I have 2 -1 charges from chlorine. And that gives me an overall -2 charge coming from chlorine. So +2 plus -2 is equal to 0. So that is my molecular formula for magnesium chloride, MgCl2. I'm gonna erase that too so y'all can see that. That's my molecular formula for magnesium chloride. Okay, last example, calcium carbonate. So calcium's elemental symbol is Ca. Carbonate is one of our polyatomic ions. Again, I don't have a great way of remembering these other than just pure memorization and note cards. But if you remember what carbonate is, it is CO3 and it has a -2 charge. So with carbonate having a -2 charge, calcium, if you look at its location on the periodic table, it's similar to magnesium. It has those extra 2, it has 2 valence electrons. So it likes to typically give those electrons away to form ionic bonds. So it typically likes to have a +2 charge. Now, adding together, as we just did in magnesium chloride, +2 plus -2, that is equal to an overall charge of 0. So this is actually our formula for calcium carbonate, CaCO3, and it becomes a neutral compound. So I hope this gives you some basic introduction to writing molecular formulas and the difference between molecular formulas and empirical formulas. And I look forward to discussing this with you all more in class.